Welcome to our channel. Today we are diving into how machine learning can help geotechnical engineers approximate engineering graphs more efficiently. Traditionally, engineers have relied on these graphs for analyzing and designing geotechnical solutions. However, finding specific design parameters, especially on log-scale graphs, can be time-consuming and prone to mistakes. Thanks to recent advancement in machine learning, we can now train models on large datasets to quickly and accurately estimate these parameters, reducing both the time spent and the chance for human error. In this video, we will explore a case study focused on assessing the settlement of a single pile. We will see how fully connected neural networks can be used to create effective machine learning models for this purpose. Let's get started. To evaluate the settlement of a single M-bearing pile, Polos and Davis 1980 provide a specific equation. While this equation involves four factors, we will focus on just one, RB, for our approximation exercise. You can determine the other three factors in the same way as RB, and I encourage you to practice that later. Now, let's take a look at RB. The graphs for RB come from Polos and Davis 1980, and show that RB depends on three independent variables: the ratio of EB to ES, the ratio of L to D, and the K value. Understanding the complex relationship between RB and these three variables through a closed form equation can be quite challenging. Instead, we can use supervised machine learning algorithms, which allow us to work with the data without fully understanding all the underlying patterns. In this study, we will use fully connected neural networks, FCNN, with the open source Python libraries, sklearn and Keras, to train our machine learning models. So, what is a fully connected neural network? It is a type of artificial neural network where every neuron in one layer connects to every neuron in the next layer. According to the universal approximation theorem, a feed-forward neural network with at least one hidden layer can approximate any continuous function to a high degree of accuracy, as long as we use a suitable nonlinear activation function. In this video, I'll be using Jupyter Notebook within the Anaconda package to develop our machine learning model. In the next session, our AI assistant will guide you through the step-by-step coding process. Stay tuned, and let's get coding.
Hello everyone, and welcome to this tutorial on building and testing a simple neural network in Python and Jupyter. Today, our goal is to demonstrate how to predict RB, a value used to evaluate the settlement of a single pile. We'll approach this as a regression problem, leveraging TensorFlow, Keras for model creation and training. The RB values we're aiming to predict come from reference charts. We extracted these data points using the Webplot digitizer tool, then stored them in an Excel file for convenience. In this tutorial, we've placed that file in a folder called Data Files, which we'll reference as we walk through our workflow. Here's a quick look at our project's folder structure. You'll see a folder named Data Files containing our dataset, and a file called Demo, IPYNB, the Jupyter notebook we'll be developing. Now, let's jump right in and start coding. To start, we import our key libraries: Pandas for data manipulation, NumPy for numerical operations, Matplotlib and Seaborn for visualization, TensorFlow and Keras to build our neural network, and several utilities from scikit-learn. We also bring in OpenPyXL for Excel file handling, Line2D from Matplotlib for optional plotting features, and finally Joblib for saving and loading our scalar. With our imports ready, let's define the path to our dataset. We store the file path in a variable called file_path and then create an Excel file object, XLS, which allows us to explore multiple sheets within the same workbook. Next, we specify the columns our model will use. We create three variables: variable_0, variable_1, and variable_2, that will serve as inputs, along with a single variable underscore dependent to indicate our target output. We collect them into a set called required underscore columns so we can easily verify that each worksheet has all the columns we need. We loop through each worksheet in XLS and read it into a temporary data frame. If any sheet doesn't contain all of our required columns, we skip it and print a warning. Otherwise, we add the valid data to a list. Finally, we concatenate these data frames into one combined data frame named df_raw and make a copy of it in df. To ensure our dataset loaded properly, we call the function df.head to preview the first few rows. This helps us confirm that all required columns are present and that the data looks as we expect. In this step, we isolate our independent variables into X and our dependent variable into Y. Because many machine learning models, especially neural networks, perform best when features are on a similar scale, we use a standard scaler to normalize our inputs. We fit and transform X, then save the scaler using joblib.dump so we can reuse it later for prediction. We choose not to scale our target variable y in this project, so we simply set y_scaled equals y. Then, we use train_test_split to divide our data into training and testing sets, dedicating 10% of the data to the test set. We also set random_state equals 42 to keep our split consistent for reproducible results. Here's where we define our neural network architecture using Keras' sequential class. We stack multiple dense layers with ReLU activations, starting with 128 neurons and gradually decreasing until our final output layer, which has a single neuron with a linear activation for regression. We compile the model using the ATOM optimizer and mean squared error as the loss function. We also track mean absolute error for additional insight. After calling model.summary to review the network structure, we train it for 100 epochs using batches of size 32, while setting aside 10% of our training data for validation. Once training is complete, we generate predictions on the test set, flatten them into a one-dimensional array, and compute three key metrics: mean squared error, mean absolute error, and the R-squared score. This gives us a clear picture of how well our neural network is performing on unseen data. To preserve our work, we save the trained model to a file called fcnn_regression_model.keras. This way, we can reload the same architecture and weights later without retraining from scratch. Let's see how our model behaves on a brand new input. We pick some random values for L/D, K, and EB/ES. Since our model expects log-transformed inputs for K and EB/ES, we use the log10 function. We then assemble these values into a small data frame called X_new. Because we used a standard scaler on our training data, we need to apply the same scaling to any new input. We load our saved scaler, then transform the new input using scalar.transform, X_new. Consistent scaling is crucial for valid predictions. Finally, we load our saved model using load_model and feed the scaled input into the model's predict method. We reshape the output to a column vector and display it. The resulting value, y_new_pred, is the model's best guess for our target variable given this new data point. And that's our complete workflow, from data loading and pre-processing, to model training, evaluation, and finally making predictions on new data. This process outlines a typical machine learning lifecycle using Python, Jupyter, and Keras. Thanks for following along, and feel free to experiment with different architectures, parameters, and data to refine your model further.
I hope you find this tutorial helpful. I have made all the raw data and Python scripts available in a GitHub repository. If you would like to delve deeper into the details of this machine learning approach, feel free to explore the material using the link provided. Thank you for watching.